Hello guys, today my topic is analysis of maximum possible sampling period for a real-time variant-based control system. I'm the first author, Bo Shang. The other co-authors are Professor Chengdong Wu, Professor Yunzhou Zhang, and Professor Yangquan Chen. First, let me introduce my university, the Northeastern University. It is a public university in the city of Shenyang, Liaoning Province, China. With an annual enrollment of over 20,000 students, it is one of the China's high-level universities designated for the state key construction of the 211 project and the 985 project. Let's get down to business. In our previous work, we found that the IFO-PD controller can tolerate a larger sampling period than the IO-PID controller in the simulation. And we think this is an important conclusion because the drones often have limited onboard computing capability. So the time period, the control period on the drones often large. And we have done a literature review to prove that the IFO-PD controller can tolerate a larger delay than the IO-PID controller theoretically. So we guess there should be some method to theoretically prove that the IFO-PD controller can tolerate a larger sampling period. So in this paper, we proposed a method that can numerically estimate the largest sampling period that a controller can tolerate and theoretically prove the IFO-PD controller can tolerate a larger sampling period than the IO-PD one. In the previous work, the experiment system is like in this picture. There is a red circle on the ground. On the drone, we have put a Pixox flight controller, an Android computer with Linux installed, and the ground station a Wi-Fi hotspot. Then the ground control station can connect with the drone by using the Wi-Fi. And a camera is mounted on the drone, facing down. So we want to control the position of the drone. And the control system model is displayed. We want the drone to hovering just above the red spot. Then we have a controller to control the speed, to give the speed set point. And then the speed set point goes to the Pixox. And then the drone moves. After that, we can use the camera to detect the red circle. From that, we can get the position feedback for the drone. But the image processing takes some time. So there's a delay, and it makes the whole control system with a large sampling period. We have used the system identification toolbox to get the plant. The plant is a second order system with the displayed parameters K and tau. We made the controller like this. It is a fractional order PD controller. So the Kp and Kd are proportional and derivative gain parameters of the fractional controller, respectively. And the lambda is a non-integral order of the integrator. So the first one is the FOPD controller, and the second one is the tuned IOPID controller. This slide shows the working period. After start, the system captures an image, and then we do some object detection, and it can detect the red circle in the image. Then the position of the red circle is put into the controller. After the controller sends the control command, the system goes to another loop. This is the sample data system stability criteria. We want to use this criteria to theoretically find the largest sampling period. Let me see the first equation. The delta t range from 0 to nh. H is the period. And for this situation, for this system, the n equals to 1. So it means the largest time delay range from 0 to the sampling period. And the first equation means we can suppose the v is a transfer function. So when the time delay influences a transfer function, the transfer function needs to change something, that is the time input. We need to change the time input from t to t minus delta t. And the second equation means if this inequality happens, the system is stable. Otherwise, the system is not stable. So we go to the problem formalization. So we formulated the problem to an optimization problem. We want the sampling period h to be maximum. So negative h should be the smallest, and that is the object function. So the inequality became a constraint. It is inequality constraint. It is not easy to calculate this constraint because we can see it wants to get a maximum value of this guy when omega belongs to range from 0 to infinite. And this one is a non-linear formula. So we formulated this calculation of fh as a separate optimization problem. And the part we want to get the maximum value became the objective function. So we can get this part. We have added a negative symbol. So the maximum became minimum. And then we got initial state and lower and upper bounds. So we can put all of those information in the MATLAB optimization toolbox. Then the MATLAB can calculate optimize the value of the objective function for the problem B. Since the problem B calculation takes some time, and to calculate each point for problem A, we need to go through the whole process of problem B. So it takes a lot of time to get some values for problem A. Because calculate 8 points for the problem for optimization A and C, and we want to see which part should be the maximum H. Remember that we want to get the maximum H that can get the FH function negative. So this figure plotted the FH, and we want to get the maximum H that can let the FH to be negative. We have plotted 8 values from 0 to 1.5, and we can see from the beginning the FH is negative until 0.7. So it seems the maximum H should be around 0.5 and 0.7. So we want to get it more accurate, and then we plotted something between 0.5 and 0.7. Then we get it more accurate. Then we plotted the part that goes across the zero line, step by step. And last, we got the maximum H for IO-PID controller. It is around 0.55 seconds, and we think this accuracy is enough for our application. Then we go to the fractional order PD controller. We need to do something complex to convert the fractional order to high order integer order functions using the outer loop method. We have chosen those parameters: the low frequency limit, upper frequency limit, fractional order, order of the finite transfer function, approximation. And then we can do those things similar in the FOPD controller to get the approximate maximum sampling period for FOPD, and it equals to 0.908. If you remember, the largest sampling period for IOPD PID controller is 0.55. So we can see the fractional order one is significantly larger than the IO-PID one in the sampling period. But we are not satisfied with that. We want to see something more detailed. So we got a index to see which one has better performance. The one we are going to calculate is called ITAE, the integral time-weighted absolute error. Then we build a Simulink model to calculate that. We simply want to get the convolution of the time consequence t and the error. After we got all the ITAE index with the sampling period, we can have this result. From the left picture, we notice that the ITAE index of the IO-PID system gets large rapidly after the maximum sampling period, which is around 0.55 seconds. I will use the very thin line to mark that. And on the right figure, we notice that the ITAE index of the FOPD system gets large rapidly after the maximum sampling period, which is around 0.92 seconds. I also marked that on the right figure. And we can see that the maximum sampling period of the FOPD controller is almost twice of the IOPID one. So we got those conclusions. The sampling period of the system was estimated using stability criteria and optimization method for both the integral order proportional integral derivative controller and the fractional order proportional derivative controller. The FOPD controller is proved to have a significant larger sampling period than the IOPID one when maintaining the same performance. So we have those future works. We'll try to use other sampling interval-dependent stability criteria to estimate the maximum sampling period. Use a multi-objective function optimization method to design fractional order controllers that can tolerate a larger sampling period. Compare sampling periods for more plants. Try to do real experiments to verify the estimated sampling period. Those are the references. Thank you. So let's go to the question part.